Good evening. I'd like to welcome you all here tonight for the lecture. My name is Neta Bakol. I'm a professor of astrophysics here at Princeton University, and I'm the director of the Council on Science and Technology of Princeton University. Tonight is the third and final Farnum lecture by Professor Alex Filippenko of the University of California at Berkeley. And it's really too bad that it's already the last lecture. I wish we had a few more of those lectures. They've been just so fascinating. And I'm sure we'll bring Alex back here for some more lectures in the coming years. The Farnum lectures are sponsored by the public lecture series of Princeton University together with the Princeton University Press. I can promise you that you are in for a real special treat tonight. And that is not only because Professor Filippenko is a spectacular lecturer, but also because the topic that he will talk about today is a spectacular discovery. It's a discovery that is one of the most surprising and important discoveries in astronomy in many decades. It was also named, as many of you know, the science breakthrough of the year in 1998 when it was first found out. The discovery, as many of you know, and as you'll hear in great detail today, that our universe expansion is accelerating, that we are expanding faster and faster with time, still amazes all of us, astronomers and the public alike. We are still trying to deal with it and understand it. And we are fortunate to have with us today one of the leaders in the work that led to this discovery, so we can hear it firsthand from the discovery team. In fact, there were two independent teams that came to the same conclusions, which is really quite impressive. Alex Filippenko is a world-renowned astronomer working on many diverse fields. You heard some of them in the last couple of lectures. Supernova, exploding stars. In fact, he runs a supernova factory where he just finds supernova, collects them, observes them, catalogs them. It's a supernova factory. He works on quasars and black holes, and he works on the expanding universe. But Alex is more than just an outstanding scientist. He is also well known for his outstanding teaching, lectureship abilities, and science popularization. He received several distinguished teaching awards at Berkeley and was voted the best professor by the students at Berkeley. You'll see shortly why he received those awards and many others. He is an enormously dynamic, enthusiastic, clear, and fun speaker. Let me tell you what some of the students say about him, and those are quotes. Best lecturer I've ever had. Alex is the man. Exclamation point. He really gets into what he's saying. He almost becomes his subject. And you will see it today, I'm sure. He seems like he is always on a sugar or caffeine high. What can be more blissful and entertaining than exploring the heavens? That's what Professor Filippenko does. And many, many more. I can keep reading those things that are just fascinating for an hour, but I'd rather let Alex talk. Alex recently won the 2004 Carl Sagan, very appropriately, Carl Sagan Prize for Science Popularization. He is co-author of The Cosmos and winner of several awards for best science textbooks, and as well as his scientific achievements and teaching. Let me just add one more thing, as many of you know, this year is the 100th year anniversary of Einstein's famous papers of the 1905, at the year 2005. It is therefore, of course, most befitting to have a lecture today by Alex on the topic of Einstein's biggest blunder with a question mark. That question mark may be removed. It probably was not a blunder of Einstein. It was probably exactly as he thought many years ago. Princeton University will have several events to celebrate this 100th anniversary this year. You can check the various events on the Princeton University website. We will have a lecture in April 6th, by Professor Brian Greene, and then we will have several public lectures in the fall as well, among many other activities. So without further ado, I suggest you all buckle up for the accelerating universe, because we are going to speed up. Professor Alex Filippenko.
Well, thank you very, very much, Netta, for that warm introduction. And this whole visit here to Princeton has been really excellent. I've had many interesting conversations with people, and it certainly has been a pleasure speaking to you these past 2 evenings. Even last night, when, of course, we had this storm come in and people came in out of the cold and found out about exploding stars. You know, I bet you they didn't expect that. But anyway, it was fun to be here. So thank you very much for the invitation from Princeton University and from Princeton University Press as well. I'm going to continue tonight along the theme that I introduced the past 2 evenings, stellar explosions and the various effects they have on the universe. But tonight I'll concentrate on how we use stellar explosions to determine the broad characteristics of the universe on large scales over large distances. And it turns out that these stellar explosions allow us to explore the universe to great depth and with greater precision than has been possible in the past. But I want to first start out by finishing up a few things that I didn't quite finish yesterday. There was a quote that I wanted to give by Mal Ruderman of Columbia University in regard to the gamma ray bursts, about which some of you heard. How many of you were in the audience yesterday? Okay, a few. So here's the quote that I had wanted to give. There were many models of what these weird gamma ray bursts might be, and theories were proliferating. And a professor at Columbia said, "For theorists who may wish to enter this broad and growing field, I should point out that there are a considerable number of combinations. For example, comets of antimatter falling into white holes." Those are the time reversal of black holes, by the way, not yet claimed. So those of you at yesterday's lectures will understand to what he's referring. I mean, we really didn't know for a very long time what gamma ray bursts were. And we still don't completely know, but we think that they are basically the birth cries of black holes. And the other thing I kind of neglected to mention yesterday was that near the end of my talk, I said that some kinds of gamma ray bursts, the short duration gamma ray bursts, may represent the merging of 2 neutron stars and producing a jet of this sort. But I think I failed to mention that when you have 2 neutron stars merge in this way, the result, we think, is a black hole, because the mass of the 2 neutron stars together is greater than what can be supported by a single neutron star, so it collapses to form a black hole. So that's just for the benefit of those who were here yesterday. And for those who weren't, I don't know, I think these lectures are being taped, so maybe there will be a way to go back and see the lecture. I know many of you couldn't make it because of the inclement weather yesterday. Okay. But the topic of tonight's talk will be cosmology. Now, cosmology is the study of the structure and evolution of the universe on the grandest scales. We're interested in questions such as, how big is the universe? What is its overall shape? What is its size and age? Okay, I mean, it might not have existed forever, all right? And indeed, we now know that it has only existed for about 14 billion years, a magnificent conclusion. What will its fate be far, far in the future? Many of you know that the universe is expanding. Will it expand forever, or will it someday fall in on itself? And then, how did the main constituents of the universe form, and how do they evolve? Those basic building blocks are the galaxies. Here's a galaxy, much like what we think our own Milky Way would look like if we could see it from the outside. A gigantic spiral galaxy consisting of hundreds of billions of stars gravitationally bound together, forming this magnificent structure that spans something like 100,000 light years in diameter. So if you were on a planet orbiting this star and you sent a radio message to a friend on a planet orbiting that star, hey, let's go and grab a beer after classes are over or something like that. It would take 100,000 years for your message to get there and 100,000 years for the reply to come back, for a total round-trip conversation time of 200,000 years. Hardly a stimulating conversation, but sorry, that's just the way the universe is built. It's built of these gigantic galaxies. And our sun is one star among tens or hundreds of billions. Now, you may have heard that there's our Milky Way, and maybe you've heard of a few nearby galaxies, but to just impress upon you how many galaxies there are and how they fill the universe, let me show you this photograph, one of my favorite from the Hubble Space Telescope, released last year. It's the Hubble Ultra Deep Field. Now, this is a tiny, tiny, but representative, typical fraction of the sky. This is like if you hold a pebble at arm's length, that's the fraction of the sky that photograph covers. It's the same fraction of the sky that the pebble subtends. All right, so it's a tiny fraction of the sky. But in this typical fraction of the sky, there's something like 3,000 or 4,000 galaxies. Let's count them. 1, 2, 3, 4, 5. I could easily spend my hour doing that, but that would be kind of boring. Remarkably, that's what astronomers are paid to do, sit around and count galaxies. It's really a cushy job. More of you should think about becoming astronomers. Anyway, there's only very few stars in our own galaxy in this picture. There's one, there's one, there's one up there. All these other smudges are external galaxies consisting of tens or hundreds of billions of stars. And this is a typical section of the sky. So, extrapolated over the whole sky, astronomers estimate that within the realm of the Hubble Space Telescope and other great telescopes, there are something like 50 to 100 billion galaxies. And that's just in the parts of the universe that we can see. We now have good reason to think that the entire universe extends far, far beyond the parts to which we have visible access. And it's filled with these galaxies. How did they form? How do they evolve with time? These, too, are central questions of cosmology. So cosmology is certainly a grand subset of astronomy. Now, before I move on, let me point out that among the lay public in general, but present company excluded, there is considerable confusion between cosmology, the study of the structure and evolution of the universe as a whole, and cosmetology, the study of hairdos and facials. They have the same root, cosmos, all that there is, or to make order of. But like astronomy and astrology, which also have the same root, they have branched off to have rather different meanings now. But this is often not understood. And to give you an example of this, here is an ad that a colleague of mine placed in my mailbox last year. Make cosmology your career. Training and supervision in hairstyling, blow drying, permanent waves, coloring and frosting. These are all very important topics, of course. Scalp treatments, body and skin care, style cuts, basic cuts. For further information and interviews, call this number. Now, classes started, last March, but I'm sure this coming spring quarter, you too can get to the cutting edge of cosmology by taking a course of this sort and learning the basics and then deciding whether you would like to make cosmology your career, as I and many of my colleagues, including Netta Bakal, have chosen to do. So look out in the newspapers and take a course. And, well, of course, these guys needed a lesson not only on the differences between cosmology and cosmetology, but they need a lesson in spelling and proofreading, because you'll notice, in addition to feather here, they have hairstying. You see that? Hairstying and coloring. Well, that's okay. That's the British spelling, and my own thesis advisor was British, so that's okay. I'll allow that. All right. Well, a central figure in this field was Edwin Hubble, after whom this Hubble Space Telescope is appropriately named. He was the first in the 1920s to pretty much definitively prove that at least some of the little fuzzy spiral nebulae that astronomers were finding in the sky are these external galaxies far from our Milky Way and gigantic systems of their own, rather than mere clouds of gas in our own galaxy from which new stars are forming. Those are exciting and beautiful, like the Orion Nebula in the Sword of Orion, but they're relatively nearby and they're not huge. Hubble showed that some of these little fuzzy spots are galaxies, and this greatly expanded the human concept of the size and nature of the universe. Perhaps even more importantly, just a few short years later, he analyzed data which basically showed that, with few exceptions, all galaxies are moving away from ours. Just a few of the most nearby ones are gravitationally bound to ours, so they happen to be not moving away. But all the others are moving away from ours. And moreover, right now, at the present time, the more distant a galaxy is, the faster it's moving away. So they're all moving away, but right now the more distant ones are moving away faster than the nearby ones. And he made this discovery by passing the light of galaxies through a prism or an equivalent contraption, producing a rainbow or a spectrum of this sort. I talked about spectra on Wednesday. Just could I see a show of hands? How many of you were here on Wednesday? And how many were not? Okay, so I'll reintroduce some of the concepts, but some of the things I discussed on Wednesday. Anyway, from a spectrum of this sort, a rainbow, you can learn all sorts of things about the object that's emitting the light, including things like its temperature and its density and its chemical composition. But in this particular case, what we're interested in is the fact that the spectrum can tell you whether an object is moving toward you or away from you along a radial direction, just along your line of sight, not perpendicular to it, and it can tell you the speed with which it's moving, okay? And this is similar to the method that officers of the law use to catch you when you're speeding. They shine a little radar gun signal at you, a radio wave, and they know its wavelength or frequency, its pitch, and they measure the frequency with which the wave comes back from your car to their little detector, and by measuring the shift in the frequency, they can figure out your speed. So, for example, if you're coming towards the cop, the pitch will be higher, and if you're moving away, the pitch will be lower. Now, I use the words pitch, which sounds like an audible signal, but it works the same way, roughly speaking, for light. So when you hear something coming towards you, the pitch is high, and when it's going away, it's low, so a siren goes like that. Well, light does the same sort of a thing. From the spectrum, you can tell how fast something is going and in which direction. Now, if you happen to hear a siren that's going that doesn't mean that the driver can't make up his mind, okay, which way to go. It just means that some sirens oscillate that way, but you can still tell that the overall pitch goes from high to low as the thing goes from approaching you to receding away from you. So what other astronomers had actually found before Hubble himself was that the spectra of all galaxies are shifted toward the redder end of the spectrum, toward a longer wavelength or a redder wavelength or a lower pitch. These things all mean the same thing. But what Hubble found was that this red shift is proportional to the present distance of a galaxy. So here are some galaxies that are only about 60 million light years away. It's pretty far, but for astronomers, that's not very far. These guys are moving away from us at something like 1,100 kilometers per second, And more distant galaxies, which look smaller and fainter in the sky in general, are also moving away, but they're moving away faster. So you can draw a diagram that looks something like this. Here we are. All the galaxies are moving away from ours, and the presently more distant galaxies are moving faster than those that are nearby. So it's like the universe is expanding, although Hubble himself resisted this interpretation for quite some time. Now, before I move on, let me pause, because there's something very odd about this particular diagram. What's strange about it? Yeah, everything is moving away from us. Why us? You know, is our Milky Way galaxy itself repulsive in some sort of way? You know, do they not like the fact that humans are in it? Do we smell? You know, is it something we said? We're the center of the universe. Yeah, it doesn't appear to be that way, you'd think, unless we're of some sort of central importance. It would be rather egocentrical to think that we're the center of the universe, right? When I give lectures of this sort at my home institution, Berkeley, or Cal, I say, are we from Stanford? You know, big rivalry. Here you could say, are we from Harvard or Yale? With due apologies to those of you who may have gotten your degrees at those fine institutions, but they're not quite as fine as Princeton, you see. So, just as Stanford is not quite as fine as Cal. Anyway, no, we don't think that these institutions are any finer than any other necessarily, or even if they are, we don't think that others are repelled from us in this way because we're of some sort of central importance. Rather, we think that if we were in any galaxy, we would see generally the same phenomenon. All other galaxies are moving away from ours. And it's easy to think up little toy models in which this property is easily satisfied. And one of my favorite is the expanding loaf of raisin bread, where the raisins are the galaxies. They don't expand. So that's because they're bound together quite strongly. And our galaxy is bound together by gravity, and we're bound to the Earth by gravity, so we're not expanding. And your own body is bound to itself through electromagnetic forces, so it isn't expanding either, despite what you might think after a large lunch or dinner. You know, maybe your body is expanding, but it's not expanding with the expansion of space, you know. So the raisins aren't expanding. Bound things don't expand. But the dough between the raisins is filled uniformly with yeast, and that causes the dough to uniformly expand. Now, I necessarily had to draw a finite universe on this diagram here, but the universe is either infinite, okay, so you don't have to worry about edges, or it wraps around itself, kind of like the surface of a balloon, in which case you also don't have to worry about the edges. So don't focus your attention on the fact that some raisins are close to an edge. That's irrelevant to the argument I'm going to make here. So let's let this loaf of bread, let's let it bake for an hour and expand by a factor of 2, all right? So you can see that from our perspective, all the other raisins moved away from us. But so too is the case from the perspective of any other raisin. All the other raisins move away. None of them can claim to be of central importance. All the raisins move away from every other raisin because space itself is uniformly expanding in all directions. Okay? Moreover, you can see that this Hubble relationship is indeed satisfied. The raisin that was initially closer to ours moved away more slowly than the one that was farther away. Quantitatively, you can easily see this. This raisin was initially 5 centimeters away. After an hour, it's 10 centimeters away. So by advanced mathematics, you find that it moved 10 minus 5, or 5 centimeters in 1 hour, for an average speed of 5 centimeters per hour. This one started out 10 centimeters away. After an hour, it's 20 centimeters away. So it moved away by 10 centimeters in 1 hour for an average speed of 10 centimeters per hour. The more distant ones move away faster simply because there's more space between us and them than between us and the nearby ones. And if each centimeter turned into 2 in 1 hour, then cumulatively, the more centimeters you had to begin with, the proportionally more do you have to end with, and so the speed looks bigger, and it is bigger. But this does not in any way mean that the galaxies are being accelerated. This is not the evidence for the acceleration of the universe. That evidence will come later. This is just evidence for uniform expansion with no unique center. If there is a unique center in our universe, it's in a different dimension. And I'll be glad to expand on that topic, pun intended, in the Q&A session following my talk. Okay, well, of interest to astronomers is the current expansion rate, and that has now been measured pretty well using telescopes like Hubble and others. We now know the current expansion rate to something like an accuracy of 5 or 10%, depending on which data you believe. But that's not the end of the story. We expect the expansion of the universe to have changed with time, and the reason for that is the presence of gravity. If I toss this apple into the air, and you can't give a talk about gravity without using the proverbial Newtonian apple, right? So I toss it in the air. On its upward journey, it slows down because of the mutual gravitational attraction between the apple and the Earth. In fact, it eventually reverses its motion and comes crashing back down. So if there's a lot of material in the universe pulling the universe in on itself, decelerating the galaxies a lot, then you could start out with a Big Bang for whatever reason. That's another lecture, okay? We don't quite understand the Big Bang. But we start out with a Big Bang, then the universe eventually reverses itself and comes down to a big crunch. Or you could say it starts out with a Big Bang, ends with a gnab-gib, which is Big Bang backwards, okay? So Big Bang, gnab-gib. So it starts out hot and dense, expands, becomes cooler, darker, but then collapses on itself, becoming dense and hot again. This is sort of an ending and a beginning in fire. But had I eaten my Wheaties this morning, I could, in principle, throw this apple sufficiently fast such that it escapes from the Earth. It never comes crashing back down. It just has to be thrown at a speed greater than the escape speed from Earth, neglecting air resistance and things like that. So that's about 11 kilometers per second. All right? So I could heave this thing, and it would never come crashing back down. But it would still forever slow down in its journey upward. And the reason for that is that no matter how far away it gets, you cannot cut off the gravitational attraction between the apple and the Earth. The apple still feels the Earth's gravity pulling it in. It's just not pulling it in enough to ever halt or reverse the motion. So it keeps going away forever. Now that's a very different fate for the universe, if the universe is doing such a thing. If it started out expanding so quickly relative to the amount of stuff within it trying to pull it back, it could expand forever, becoming ever more dark, ever colder, ever more dilute, expanding eternally. All right? That's a very different fate from the ultimate collapse. And I said that one of the central issues of cosmology is the future of the universe. What will become of it in the future? So we would like to know whether it will recollapse, ending with a gnab-gib, or expand forever. The way to tell is to measure the history of the expansion rate. After all, if you measure the universe to be slowing down quickly with time, then it will probably stop and reverse its motion. In fact, it's not even a probabilistic argument. You can use equations to determine whether it will do so. Okay? And if instead it hasn't been slowing down very much, then in fact it'll probably expand forever. So the key to determining the fate of the universe is to measure the past history of expansion and see whether it's been slowing down a lot or only very little. Now you might say that that sounds good, but how are you ever going to figure out or measure the past history of expansion when we live right now and can't see into the past? Or can we? Maybe there is a way of looking back into the past, just as paleontologists look at different strata of the Earth and see dinosaur bones and the bones of other creatures in different layers and figure out the past history of life on Earth by looking into the recorded history in the rocks. Maybe there's something similar that's astronomical.
in nature? Anyone venture a guess of what that might be? Yeah.
By looking by light, it takes a long time. If you look somewhere real far away.
There you go. If you look somewhere really far away, it's going to take light a while to get there. That's right. What's your name? Alexander. Hey, my name's Alex, but it's not Alexander. So anyway, Alexander is right. Light travels fast, but not infinitely fast. In fact, it travels about a foot per billionth of a second, a foot per nanosecond. So Alexander's about 10 billionths of a, well, he's about 10 feet away from me, so I'm seeing him as he was in the past 10 billionths of a second ago. He might not even be here anymore. He is, you know. Good for me, I have a larger audience and a perceptive student. Even better for him, he's still on this good earth, okay? We see the sun as it was a little over 8 minutes in the past because it takes a little over 8 minutes for light to traverse the 93 million miles, 150 million kilometers between us and the sun. You see even the brightest stars in the sky as they were a few tens of years ago, because the typical bright stars are a few tens of light years or hundreds of light years away. So you're seeing them as they were in the past. Now, if we look at galaxies that are billions of light years away, we're seeing light from those galaxies that originated billions of years ago. So maybe 1 billion light years away. We can turn the lights down now again. And maybe 4 billion light years away, and 7, and this little smudge might be 10 billion light years away. Encrypted in that light from those galaxies is information about the expansion rate 1 billion years ago, 4 billion years ago, 7 billion years ago, and 10 billion years ago. So if we look at all these galaxies, we can measure the history of the expansion rate because we're seeing light from long ago. It's like the geologic strata. Now you might say, okay, well that sounds good, but again you've got a problem, because how are you going to know if this galaxy is 4 billion light years away, or maybe 3.5, or 4.7, or something like that? You know, this measurement of the change in the expansion rate is likely to be a subtle effect, so you'd better have accurate distances. The way we normally get distances of objects like galaxies is by finding a star in a galaxy whose properties we know and we've measured really well for stars in our own galaxy. You might think that all the stars are the same, but there are different kinds of stars, and there are certain kinds of stars that we recognize as being, you know, particularly well measured. And if we find the counterparts of those stars in distant galaxies, and we measure their apparent brightness, and we know how powerful such a star really is, then by making the comparison of the apparent brightness and the known true power, we can determine the distance of that star and hence the distance of the galaxy in which it's located. Now, you use this effect all the time when you judge the distance of an oncoming car at night. You look at how bright the headlights appear to be. You've calibrated the true power of the headlights of a car at a known distance, maybe 6 feet away, and you make this comparison of how bright the headlights look. And you do this calculation in your head. Even if you don't think you're doing a calculation, you are. And if you're not very good at doing this, then you shouldn't be driving at night, you know, because you'll misestimate the distances of cars and you'll get into accidents. So you don't have to be doing an equation in your head. You become accustomed to this kind of calculation, but that's what you're doing. So the thing to do is to find individual stars in these galaxies and measure how bright they appear to be and compare them with local counterparts. But again, you might say, well, you're foiled, because in these distant galaxies, billions of light years away, the stars are really faint and they're blurred with many, many other stars, even with the wonderful clarity of the Hubble Space Telescope. So you might say, you can't see individual stars in these little galaxies. Well, in general, you're right. But there is one kind of star you can see individually billions of light years away. Anyone know what that kind of star is? A supernova, right. So I talked about them on Wednesday. This happens to a small minority of stars, but a few of them violently destroy themselves in a blinding flash of light at the end of their lives. Our sun will not do this. Maybe one star per galaxy per century will choose this kind of death, dictated, of course, by physics. It's not itself choosing what to do, but physics determines what happens to a star. And when it does explode, it can become 1 billion times more powerful than the sun. So I gave this analogy on Wednesday, but if the sun were to do this, which it won't, you would need sunblock of 1 billion to protect yourself, or supernova block 1 billion to protect yourself. So they're amazingly bright things. And you can find them by taking pictures of galaxies and looking for arrows. And when you do this, you find that there are these exploding stars in galaxies. And we used to give degrees for this kind of work, and now it's child's play almost. Well, as I described on Wednesday, it's not really quite so easy. We don't force our students to look through telescopes at galaxies and memorize the shapes and sizes. Instead, we take pictures of galaxies with a robotic telescope, as I discussed on Wednesday, and we find many, many such exploding stars. And we do this with a little robotic telescope that my team built in Berkeley. And then we analyze those exploding stars, and again, those of you who were here on Wednesday will know a little bit more about this than what I'll say right now, but basically they come in 2 types. Those without hydrogen in their spectrum, where by the spectrum, again, I mean the brightness of the light versus color or wavelength. Just plot up the brightness of the light in that little rainbow I showed you. So there are those without hydrogen, and there are those with hydrogen. And these, by the way, are elements that were synthesized during and prior to the explosion. These are the elements of which life exists, itself exists, Part of us is made of iron and stuff. Not much, we're still mostly hydrogen and things like that, but there's a lot of oxygen in our bodies, and there's calcium in our bones. These elements were cooked up in stars, and I described that process on Wednesday. But the point here is that the so-called type 1s, and in particular the type 1As, are a very uniform kind of star. We think they come from a bizarre kind of a star called a white dwarf, which is what our sun will turn itself into in about 6 or 7 billion years. But in the case of our sun, it doesn't have a companion, and so it'll stay as a white dwarf in a fairly stable configuration for billions upon billions of years. But some white dwarfs are bound gravitationally to another star from which they can steal material and gain mass. And these kinds of stars, made out of a weird matter called degenerate matter, become fundamentally unstable when they reach a certain limiting mass known as the Chandrasekhar limit. And at that limiting mass, roughly 40% bigger than the mass of our sun, they become unstable, and one of the ways in which they deal with this instability is by exploding. And they become this gigantic flash of light, as you can see here. They brighten, and then they fade. And it takes a few weeks for them to brighten and a number of months to fade. I've sped up the process here so it wouldn't be very boring. But the point is that since the white dwarf is a very particular kind of star, and since it blows up always when it reaches a certain particular mass, and it's the same mass every time, and it blows up in basically the same way every time, these things reach the same peak power. So they're like 100-watt light bulbs. They're much more powerful, of course, but they're like 100-watt light bulbs. And maybe they vary a little bit. Maybe some of them are 85 watts, and maybe some are 113. But to make a long story short, we have a way of reading the label on the light bulb and even telling by how much these things differ from 100 watts. We can tell whether they're slightly overluminous or subluminous, overpowerful or standard. So the point is we know how bright this light bulb gets at its peak. And if we find a bunch of these things in nearby galaxies whose distances have already been independently measured by other astronomers looking at other normal kinds of stars, with superb photographs, you can actually tell the distance of this galaxy by measuring structures within it and comparing with similar structures in our own galaxy. So we know how far away this galaxy is. We measure the peak brightness of the supernova, And from knowledge of the distance and the peak brightness, we therefore know the true power, the peak power. So that's like you've figured out the power of the car headlight that's near to you, distance you've known, you've measured independently. So we measure a bunch of these guys in galaxies of known distance. Then we say, aha, let's find their counterparts in these tiny, faint, fuzzy little galaxies that are billions of light years away. So now I get to the cosmology, okay? So now you go to big telescopes, not like my little tiny one, and you take deep pictures of the sky. By deep, I mean you go to faint limiting brightnesses. These faint little things are far, far fainter than can be seen with small telescopes. And most of these little fuzzy things are external galaxies. They easily outnumber stars in our own galaxy when you look in a given direction. Maybe that's a star, maybe that's a star. But all these other things are galaxies. And if you use large telescopes to take many photographs of the sky like this during the course of a given night, you might sample in all of those photographs up to 100,000 galaxies, because there are several thousand in this picture alone, and you take multiple pictures of different parts of the sky. So easily in one night, you can take the mugshots of 100,000 galaxies. If you then repeat those same fields 3 weeks later, among 100,000 galaxies, a whole bunch, a few dozen, you can figure it out, will have produced an exploding star in the intervening 3 weeks. So you compare the new pictures with the old ones and see how they have changed. And here is a small, oops, I guess I didn't show it, but if you subtract one image from another, you will see that there's just nothing. There's zero signal left over. But occasionally there will be some little blip which is new in the new images and wasn't there in the old images, and that becomes a supernova candidate. Actually, I do think I show that slide in a couple of slides. So about 10 years ago, a little bit more than that actually, two teams of astronomers decided to look for exploding stars that are very distant, measure their peak brightness, compare that measured brightness with the known power of nearby ones, hence get the distances of the galaxies, and hence we would know how far back into the past we are looking in order to then decipher the expansion history of the universe. And these two teams are the High Redshift Supernova Search Team, led by Brian Schmidt at the Australian National University, and the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley Laboratory. And contrary to popular opinion, we're not always at each other's throats. It has been a healthy, spirited competition which, if you'll pardon the pun, has accelerated progress in this field because each of us wanted to be first and we wanted to be the best. So if some other team is taking all sorts of subtle effects into account and you, as an astronomer, are not, you will look bad in comparison to the other teams. So you want to do the science as well as you can, and there's nothing better than having another group trying to do the same thing, okay? So both teams, I think, did their work very carefully and came to essentially the same results. They used, admittedly, the same technique, so you could question this technique, and I will show you near the end of my talk how other techniques are now leading to similar conclusions. But here's the slide I wanted to show of a small subset of one of those wide fields where on the 7th of April, here's this galaxy. On the 28th of April, 3 weeks later, that same galaxy is present, but the sharp-eyed observer will notice a little tiny protrusion here, which when you subtract this image from that one, shows up fairly clearly. And then, of course, in a Hubble image, you can see it without even doing any subtraction. The Hubble is just a wonderful device, and I very much hope that Congress provides the money to service it one final time with a crew of astronauts, which I feel is a reasonably safe thing to do, especially if they plan to go to the International Space Station anyway. Okay, so here then is a supernova candidate. Of course, other things can masquerade as supernova. You have to make sure you've got a supernova, and that's where I come into play. I use the biggest optical telescope in the world. There's actually two of them. The Keck telescopes on the Mauna Kea volcano in Hawaii. These are giant pieces of glass, 10 meters in diameter, and with these big telescopes, we can take a spectrum of the feeble light from this distant supernova candidate and see whether it really is a supernova or not. Now, you might question astronomers' judgment in building telescopes on the top of a volcano, but the geologists at Cal and Caltech and elsewhere tell us that Mauna Kea is an extinct or at least a highly dormant volcano. Well, they'd better be right, because among a bunch of institutions, there's about $1 billion worth of equipment on top of this highly dormant volcano. And, you know, it doesn't give us a good feeling where occasionally we see Mauna Loa, the volcano next door, 10 miles away. It erupts every 20 or 30 years. And Kilauea at the southeastern end of the island is arguably one of the world's most volcanically active regions. But the geologists tell us that the tube underneath Mauna Kea is all clogged up and the magma is coming out elsewhere. So anyway, we hope they're right. If they're wrong, of course, we will fire them, even those who have tenure, because some crimes are so egregious that even a tenured professor can and should get fired. So, well, when these supernova candidates that my team colleagues find for me are confirmed as supernovae of type 1a, the good kind, the other kinds that I talked about on Wednesday and Thursday aren't so good for cosmology, well, then, of course, you know, we get these spectra that show us that undeniably this is a supernova of type 1a. Here's brightness versus wavelength, and this is just a beautiful case of a high redshift supernova that looks just like a nearby one, and that makes me a very happy camper. And now you can see the real reason we build observatories in Hawaii. I do live in California, but I live in Northern California, where the water is too cold for bathing for my taste. So I like Hawaii as much as anyone else does. Now, occasionally the airline pilot says, you know, there's Mauna Kea, one of the world's greatest sites for an observatory. It is said that there are 360 clear nights per year on Mauna Kea. Well, if that's the case, then I get all 5 of the bad ones each year. You do not get 360 clear nights. I mean, this place, in fact, is in the tropics, but it's so high that it occasionally even snows up there. And one observing run a few years ago was particularly bad. There was a huge snowstorm during the first few nights that I had, so there was no chance of opening the domes. Okay, I didn't question this. You know, you couldn't see the sky, right? You couldn't see stars. But a few nights later, the sky cleared off. Unfortunately, there was a stiff wind blowing, and it blew the snowflakes off of the ground, and it, you know, would have deposited them into the dome had the operator opened the dome for me. So no matter how large a green bill I waved in front of the telescope operator, he wouldn't open the dome. And that was incredibly frustrating, because I could have taken excellent data that night. The wind doesn't hurt you that much, but of course the snow can ruin the telescope. So the operator was doing his job, keeping the telescope safe from astronomers such as myself. You know. So you can become all depressed and stuff, or you can make lemonade out of a lemon and do something else. And so what you can't do is ski from the summit of Mauna Kea all the way down to the beach and then jump into the ocean, because even in the coldest of years, the snow goes only about 1/3 of the way down the summit. Okay, so we find a bunch of these things, and we take snapshots of them, and we watch them brighten, and then they watch them fade, and we measure their peak brightness. And here's the first punchline, basically. All right? Here are 3 supernovae with zoomed up shots shown there, of course appropriately marked with arrows. And these exploding stars are incredibly faint. Now you might say, well, big deal. You were trying to find exploding stars in distant galaxies. Of course they're going to be faint. Yeah, well, they're too faint. They're fainter than they have any right to be. Now, let me carefully explain that. If I could have the lights on a little bit. Let me give you an analogy. Suppose I toss this apple up, and that's the expansion of the universe. And suppose, just for argument's sake, the age of the universe is only 1 second. So after 1 second, I measure the height of this apple above my hand, and it's some distance, okay? Now, if there were less gravity here on Earth, and I can't make the Earth have less gravity, so I'll do the next best thing. I'll toss this apple faster. If I toss it faster, which is sort of like the Earth having less gravity, the apple decelerates less in 1 second, and so it travels further in 1 second than it would have when it was slowing down a lot, right? Makes sense. If it's slowing down less, it travels a greater distance in the same amount of time. Now, suppose there were no gravity at all. Then I toss this apple, and there's no reason for it to slow down at all. That's just Newton's first law of motion. You toss something, and it keeps on going with the same speed in the same direction forever, unless acted upon by other forces. So, in fact, an apple with no gravity goes at a constant speed, doesn't slow down, and in 1 second it gets to an even bigger distance, right? But you can't get any further than that, right? You're either slowing down due to gravity, or there's no gravity, in which case you're not slowing down and you reach some maximum distance in 1 second. Well, we found that these supernovae are so faint that the derived distances imply that the apple is farther up than it could have reached in 1 second, even if there were no gravity at all. Okay, so it gets farther away than it could have gotten even with no gravity at all. So that suggests that it did what? It accelerated, right? If you attach, for example, a rocket to this apple and you release it, it goes zoom, and it can get higher up in 1 second than if it were just tossed with a constant speed. Now, you can question whether other things are going wrong, whether there's other interpretations, and we could get into that later, but suffice it to say that after much gnashing of teeth and all that, we could not find anything wrong with our methods for taking data or analyzing the data, and we didn't see that any other influence was leading to a wrong conclusion. So we tentatively announced in early 1998 that we had measured evidence for acceleration, not deceleration, okay? And so the headlines that came out were, astronomers see a cosmic anti-gravity force at work. We use the term anti-gravity hesitantly because reporters catch wind of this and they then ask, well, can we attach this stuff to automobiles and levitate over San Francisco Bay Area traffic jams or New York City or something like that? You know, or is this the way that astronauts made anti-gravity boots? Well, first of all, astronauts didn't have anti-gravity boots. It's just that the gravity on the moon is less than on Earth, and so you can kind of hop around, you know, more on the moon. But anyway, this is a non-local effect. You can't attach it to yourself or your car or anything like that. But it has an effect over billions of light years of empty space that's analogous to sort of a repulsion, an anti-gravity, okay? And our own team leader, Brian Schmidt, said, my own reaction is somewhere between amazement and horror. Amazement because this is not the answer we expected. After all, we set out to measure the rate of deceleration, and instead we found that it's accelerating. And horror because at that time we still weren't absolutely certain that we're right. And, you know, if we were wrong in some horrible way, like our computer program had the equivalent of 2 + 2 = 5, that would be a huge embarrassment. And, you know, science doesn't progress from errors like this. Science does, however, progress from errors in interpretation that turn out to be subtle and which turn out to teach you something interesting about the universe. So if we were erroneous, we were hoping that it would end up teaching us something interesting about the universe. But we still didn't want to, you know, lose our funding and stuff, because this could be the kiss of death, right, for any scientist. And on our own team, the person who first realized what the data were trying to tell us was a young postdoctoral scholar at the time working with me at Berkeley, Adam Rees. He would come to my office every few days showing me the results of his measurements of the faint supernovae. And I said, Adam, this can't be the right answer. Go back to your office and learn how to measure the stars properly, you know. But, you know, he's a bright guy, and I could tell after a while he hadn't done anything wrong. And other people on our team reproduced his measurements independently. And we knew that the other team was coming up with some sort of a strange result. We didn't know what result, and they knew we were coming up with some sort of a strange result, and this is about the strangest result you can think of. So both teams decided to announce their results essentially simultaneously in February of 1998. Now, by the end of the year, as Netta mentioned, the editors of Science magazine proclaimed this to be the single most important discovery in all areas of science that year. And we were very honored and thrilled by this, by this Breakthrough of the Year award, but we were still not completely sure that we're right, because this was a radical announcement, right, to be sure. But they said, look, there's been the better part of a year for people to analyze your data, shoot any obvious holes through your arguments, and no one has yet found any obvious flaws. So either this is right, or if it turns out to be wrong, it will end up teaching us something interesting. So they decided that it's deserving of this honor. And the caricature of Einstein here is surprised, not because he's blowing universes out of a pipe. You might not have known that that's where universes come from, but that's where they come from. Not really, but there could well be multiple universes, and I'll be glad to come back and speak about that topic someday here in Princeton. But he's rather surprised because this single universe that he blew out of his pipe is increasing in size at a faster and faster rate, which is quite antithetical to the expectation from normal gravity. He's doubly surprised because he has a sheaf of papers here on which there's an equation. Lambda, whatever that is, equals 8 pi times Newton's constant of gravity times the density of the vacuum. Now, what in the world does he mean by the density of the vacuum? You were taught on your mother's knee, I hope, not just that E equals mc squared, but that the vacuum is sheer emptiness. It's nothing, zilch, nada. It should have zero energy density, energy per unit volume. So what does he mean by the energy of the vacuum? Seems like nonsense. Well, in 1917, shortly after developing his general theory of relativity, Einstein felt forced to introduce a mathematical fudge factor, which was not mathematically incorrect, but it was disturbing to him because it had no independent laboratory evidence for its existence, and it didn't really make much sense, and it implied a non-zero energy for the vacuum. And he felt compelled to introduce this because at the time, people didn't know that the universe is expanding, nor did they think that it was collapsing. People thought that it was static, neither expanding nor collapsing. This is 1917, 12 years before Hubble's discovery of the expanding universe. Because gravity of a normal nature is always attractive, people felt that, well, all the galaxies, or, well, they didn't really know about galaxies back then, but stuff should all be pulling on other stuff. And so, if anything, the universe should be contracting, perhaps even collapsing in on itself. And it didn't appear to be doing so. So Einstein said, well, let there be some unknown repulsive effect, lambda, which exactly counterbalances the attractive force of gravity. So this force of gravity pulls one galaxy toward the Milky Way. If this repulsive effect is exactly oppositely directed, and even more peculiar, has exactly the same size, so this up arrow has exactly the same size as this down arrow, then they will cancel each other out. Just like when I hold this apple here, gravity is pulling down on it, but my hand is pulling up with exactly the same force, so the apple is stationary. If I let go, gravity dominates, the apple falls. If I pull up harder than the attractive force of gravity, then the apple goes up. But if they're perfectly tuned, and my muscles know how to do that, then the apple is stationary. So he said, let there be this effect that is perfectly tuned. And he had no physical origin for it. It seemed arbitrary. He didn't like it. It was not aesthetically appealing. He never liked this cosmological constant lambda, but he felt compelled to introduce the term into his equations of general relativity. Now, 12 years later, when Hubble discovered that the universe isn't static after all, it's expanding, The whole physical and philosophical motivation for this weird effect disappeared. The universe could have begun its life in an expanding state for whatever reason. We don't understand yet, but let it be. Then no additional forces are needed to continue that expansion. It just keeps on expanding on its own. So forget the cosmological constant and anti-gravity. Einstein renounced the idea as the biggest blunder of his career. Had he not introduced it, he would have predicted, as a few other theoretical physicists did do, that the universe is more likely to be in some sort of a dynamic state, either expanding or, more likely, collapsing due to gravity, but not this unusual state of being static and finely tuned. So here Einstein is sad that he ever introduced the idea of repulsion, of a cosmic nature. Now, what have we done? We have resurrected the idea, not to make a static universe, but rather to make one which, over the largest distances, is accelerating. So what we're saying is, not in this room, not in our solar system, not in our galaxy, not even in our local cluster of galaxies, but over the largest scales, billions of light years of mostly empty space, there's an effect whose magnitude, whose size, is slightly bigger than the attractive force of gravity. Here in this room, obviously, that's not the case. But over the largest scales, repulsion dominates. So Einstein's blunder was not the idea of cosmic repulsion. That, we think, has been resurrected. His blunder was a much more trivial one in that he made the size of the up arrow exactly equal to the size of the down arrow, and that was the unlikely thing, you know. More likely they will be mismatched in some way, and so you'll either have cosmic repulsion or attraction. So that's not so much of a blunder, you know. The idea, it turns out, was brilliant and probably right. So I don't know what Einstein's reaction would be if he were alive right now and would hear about this, but perhaps his reaction would be something like this. I don't know, you know. Okay. So initially, when we announced this, we were greeted with considerable skepticism, as should be the case. In science, we're bred to be skeptics. But gradually, I don't have time to tell you the details, Einstein's repulsive or repugnant idea caught on because more and more evidence began supporting it. And I do want to have time to show you some of that evidence. So the idea caught on, and now people are not working on the problem of whether this effect exists. Most physicists and astronomers accept that it exists. Now the name of the game is to figure out what is causing such a weird effect. And many think that it's the number one problem in all of astrophysics, not necessarily in astrobiology, which is a different subject. You know, is there life in the universe elsewhere? That's a very interesting subject. But in astrophysics, what is the nature of this energy or force? And some think that it's even the number one problem in all of physics, because the resolution of this problem may well affect our understanding of the forces of nature and the properties of particles and fields at their most fundamental quantum level. So many people are now working on this. If the effect is some kind of a property of space that doesn't change quickly with time, then we can make a very clear prediction. Long ago, when galaxies were close together, the effect of repulsion should have been negligible for two reasons. Galaxies were close together, so their gravitational attraction for each other was bigger than when they're far apart. Okay? Gravity is stronger when things are closer together. So gravity was bigger long ago. Moreover, the space between the galaxies was smaller. So the cumulative effect of whatever this repulsion is would have been smaller long ago than it is now when the spaces between the galaxies are big. So long ago, the universe should have been slowing down in its expansion. And then eventually, when it became dilute enough, the repulsion overtook normal gravitational attraction and the universe started accelerating. So it should have been decelerating for the first maybe 9 or 10 billion years, and then the last 4 or 5 billion, it should have started accelerating. So to test this hypothesis, we should look back further in time than the 4 or 5 billion years on which we based our first conclusions. If we look at exploding stars that are 8, 9, or even 10 billion light years away, we should see cosmic deceleration, and only more recently, acceleration. So in the past couple of years, we've done the first stages of this experiment. We've measured a whole bunch, about 10, not a whole bunch, but about 10 very distant supernovae, and from the analysis of their light, we can tell that long ago, back then, 10 billion years ago, the universe was indeed slowing down in its expansion. And only 4 or 5 billion years ago did repulsion begin to dominate. So it went from deceleration to acceleration. A change of that sort mathematically happens to be known as a jerk. So we measured the cosmos to be going through a jerk, kind of like a cosmic jerk. And when the reporters found out about this, they came up with headlines like this: a cosmic jerk that reversed the universe. Now, you know how it is with newspapers. You never read the whole thing. You look at the headlines and you look at the picture. And then, if that's sufficiently interesting, then you read the whole article. So I started receiving phone calls. Hey, who's this cosmic jerk you work with who reversed the expansion of the universe? Well, it doesn't say who reversed the expansion. It says that reversed. So anyway, Adam's mother was not very pleased with this juxtaposition. But okay. So our latest results, based on over 200 supernovae, is that our universe is filled with some sort of a dark energy, as it's now called, which causes this repulsion. And that's a regrettable term because, as many of you learned, E equals mc squared. Here in Princeton, of course, everyone should know that, right? The home of Princeton, the home of Einstein for so many decades. And so you learned that energy and matter are in some way equivalent. So is dark energy in some way the same thing as dark matter, about which many of you have heard? Absolutely not. They're the opposites of one another. Dark matter pulls, dark energy pushes. All right? Anyway, so that's too bad. But this repulsive dark energy now, in fact, is the dominant stuff of the universe. And in second place is dark matter of a kind whose effect we see, but whose origin and properties are really still kind of foreign to us. We don't really know what most dark matter is. And the kind of atoms of which we are made constitute only 4% of the universe. We don't know what 96% of the universe consists of. We just know that it's either gravitating or anti-gravitating, but we don't know what it is. That's kind of disconcerting, isn't it, right? 96% of this room is stuff that you don't know of? Well, that's not true, it turns out. 96% of the universe is stuff that we don't know of. But most of the universe is basically empty space filled with this other stuff. Here in McCosh Hall, space is filled with air and me and you, right? So we know what's in this room, we think. But anyway, applied to the whole universe, dark energy and dark matter dominate. So you might say, this is such a preposterous universe that is there any other evidence that what I'm saying is anything beyond just stuff from Berserkly? And I've almost run out of time, so let me cover this last part rather quickly. There was a great discovery made here in New Jersey by Arno Penzias and Robert Wilson. They were using a radio telescope owned by AT&T Bell Labs to study radio emission from space. And they found that after they had calibrated away everything else, there was left over a slight hiss, a source of noise that they couldn't get rid of. Okay, and they scraped away the pigeon dung on their horn and everything else, and the noise was still there. You can actually see a little bit of this when you tune your television to a channel that doesn't happen to be broadcasting anything at the time. So you just see this meaningless noise on your television set. And where you see this, oops, oh yes, the meaningless noise that I meant to show you was this here. A few percent of these speckles are this radio radiation coming from the cosmos, it turns out. What they discovered was the afterglow of the Big Bang, showing that the universe did begin its existence in a hot, compressed state. And in fact, George Gamow and his associates predicted the existence of this cosmic microwave background radiation in the 1940s and early 1950s. More detailed studies and a rediscovery of this effect was done here at Princeton by Bob Dickey. He happened to be unaware of the earlier work which was published in Soviet journals, and he sort of rediscovered this effect, and his student Jim Peebles, a professor of physics here at Princeton, did some detailed calculations suggesting that the current temperature of the universe should be about 10 degrees above absolute zero when averaged over all of space. And it turns out that Dickey then he did persuade David Wilkinson and Peter Roll to try to detect the afterglow from the Big Bang. So they set out to measure this predicted radiation. Penzias and Wilson turned out to have found it already, unbeknownst to them. They were told what their discovery means, but they made the discovery first, so they won the Nobel Prize. And arguably, some of the theorists should have won the Nobel Prize as well, but they were very careful experimentalists. They discovered the afterglow of the Big Bang, and they won the Nobel Prize for this very, very important work. Okay, well, I will show you a map of this radiation, and it will be a map of the entire sky, kind of like this is a map of the entire Earth. And what I'll show you is a map of the temperature of the entire sky, just as here, in various shades of orange and blue, we show different temperatures. Generally hot in equatorial regions, generally cold near the poles. To a first approximation, the radio radiation is absolutely uniform, with a temperature of about 3 degrees, close to Jim Peebles' prediction, but a little bit less. So it's very uniform. But if you look very, very carefully, using telescopes sent up in gondolas on balloons in very dry areas like the Antarctic, and also telescopes sent up with satellites, then you find that there are tiny fluctuations in the temperature. Some parts are a little tiny bit hotter than average, and other parts are a little tiny bit colder by a few parts per 100,000. This is a tiny effect. And these fluctuations are associated with inhomogeneities, variations in the density of the universe at early times, from which the magnificent clusters and superclusters of galaxies that Netta Bakal and others here study, these structures arose from these tiny variations in the density, which are seen as variations in the temperature. I'm going a bit fast, but I'm trying to end here, and some of you I know from your questions the past few evenings know quite a lot of astronomy, so I thought I'd tell you this. Well, we can calculate the expected physical size of the density variations that existed back then, long ago. Their observed angular size tells us something about the geometry of the universe and something about its overall density. And the reason for that is that depending on which kind of geometry our universe has, light rays, like those emitted by this giant slug-like thing, travel along different paths. In a universe that's perfectly flat, by which I mean the laws of Euclidean geometry are perfectly satisfied, light rays that are initially aimed parallel to one another remain parallel. But there are other kinds of geometry that there could be, spheres, or like horses' saddles, sort of like, okay, not quite, like Pringle potato chips. And there, the light rays travel along, initially diverging and then converging rays, or rays that diverge quite a lot. And so it turns out that depending on the geometry of the universe, a meter stick or any other structure of known physical size will have a different angular size, will have a different size as seen in the sky. So in a flat geometry, the angle subtended by this meter stick will look like that. In a positively curved spherical geometry, it will look bigger. The angle will look bigger because the light rays did this kind of a thing upon entering or before entering your eye. And in a negatively curved geometry, like a horse's saddle, the angle is smaller because the light rays do this kind of a thing. What astronomers have shown is that the angular size of those fluctuations is most consistent with a flat geometry, with a geometry where on large scales light rays travel along their Euclidean paths. And this was beautifully shown with the Wilkinson Microwave Anisotropy Probe satellite launched a number of years ago and whose first-year results were announced a little while ago. This is the map of the sky measured by this satellite named in honor of David Wilkinson of Princeton University. And this map shows beyond any shadow of a doubt, I would say, that the geometry of the universe is flat. And that requires that the density of the universe be far greater than what is given to us by atoms alone and by dark matter. There's got to be other stuff out there. And through a rather complicated chain of reasoning, we also know that this stuff cannot consist of normal atoms or normal cold dark matter. It's consistent with, in fact, dark energy of a repulsive nature. So this is completely independent of supernovae, and I thought it particularly important to spend the extra time that was necessary to describe this here at Princeton because so much of the seminal work was done at Princeton. Well, so then what is this dark energy? What is this repulsive effect? It's clearly not the luminous material in the universe because that pulls. It doesn't push. It's also not the dark matter. See, there's dark matter all over the place. There, and there. Dark matter was first postulated by Fritz Zwicky, the fellow whose photograph I showed you on Wednesday. For those that weren't here, he was a brilliant guy at Caltech, but he was arrogant as all heck. He didn't have a high opinion of his colleagues at Caltech, and he called them spherical bastards, because they're bastards any way you look at them. Anyway, he was a brilliant guy who came up with dark matter, and whatever this stuff is, it can't be dark matter either, because it has to push and dark matter pulls. So we now call it dark energy. We don't know what it is. Some people have called it quantum energy, funny energy in the univere. You see, theoretical physicists sometimes don't know how to spell. But anyway, cosmologists ponder the missing energy. It's not missing, it's there. We just don't know what it is. There are hundreds and hundreds of theories. The simplest example still goes back to Einstein's concept of the cosmological constant, but of unknown physical origin. One possible physical origin is that this stuff consists of quantum fluctuations in space itself, which we know to exist because these fluctuations in the energy and in the matter content of empty space actually affect, to a slight degree, the structure of atoms. We know that these things exist. We know back from the time of Feynman and others, 40 years ago, that the vacuum itself is roiling with activity. But it had always been assumed that for every positive fluctuation of this sort, maybe the energy is borrowed from space, leaving a negative energy hole, so that on average, it all averages out to zero, leaving zero energy for the vacuum. Well, maybe, just maybe, by some principle of super-duper symmetry that fails at some subtle degree, maybe the positive energy fluctuations slightly outnumber the negative energy ones. If so, the effect on space would be a cosmic repulsion. So this is one of the hundreds of theories, but keep your eyes and ears open. I'm sure there will be many things about this in the future. So how will then the universe end? We don't really know, because we don't know what the properties of this dark energy really are at the fundamental level. However, we can say that if the dark energy remains repulsive, then the fate of the universe is quite clear. It'll expand forever, easily, faster and faster and faster, approaching an exponential rate, doubling in time, doubling in size for every increment of time. But it could someday become attractive, in which case the universe could still recollapse on itself. But if it remains repulsive, and if you want to see galaxies like this with your very own eyes through a telescope, you'd better do it in the next few tens of billions of years, because beyond that time, the galaxies will have been whisked away beyond the realm of any conceivable telescope. So if this stuff exists and continues to be repulsive, the universe will expand forever, ending in a cold, dilute, dark, icy death. And Robert Frost apparently knew of these two possibilities: an ending in fire, recollapsing to a high density, a high temperature, or an ending in ice, expanding forever, becoming cold and dilute and dark. He might not have known about anti-gravity, in fact he probably didn't, but he knew of these two possible fates for the universe, because he had this great poem, Fire and Ice. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if I had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So Frost would prefer the recollapsing universe, an ending in fire. But if he had to perish twice, eternal expansion wouldn't be so bad, an ending in ice. And that's perhaps appropriate, given his name, Robert Frost. Thank you very much. I'll be happy to answer questions. And I thank you for bearing with me for going over time. By the way, again, some people yesterday asked me whether I have any taped lectures, and I do, with the teaching company. You can contact them at teachco.com if you're interested in taped lectures on cosmology and astronomy. So I'm willing to answer questions as long as we'll take it.
Thank you very much.
Okay.
As I told you, a fabulous lecture on a fabulous topic and questions now.
Maybe what we could do is do 10 minutes of questions, then let people make a graceful exit, and then I'll be happy to answer questions for longer than that. Yes, there was one right there, yes.
I didn't want to ask a question. I just wanted to ask about Robert Frost and mention that another poet, T.S. Eliot, remarked on the same subject.
T.S. Eliot remarked on the same subject.
It would say that the world would end.
I see. I should look up T.S. Eliot's poem. I should look it up.
Oh, okay.
Good, thank you. Yes.
It seems at the moment that the black energy, is dominating, that will increase the rate of expansion.
Yes.
Will the rate of expansion reach a point where it reach the speed of light?
Oh, well,
if it happened, what happened then?
Thank you for your question. The question is, with this accelerating expansion, will the expansion reach a point where it exceeds the speed of light? And is that even possible, given that, relativity says, supposedly, that nothing travels faster than light? It turns out that relativity is often misinterpreted. What special relativity says is that no particle, or specifically no information, can travel through space at a speed faster than light. But space itself can expand faster than light. And Alexander, if you'd come up here with me and help with this little demo here, let me show you. By the way, I'll give you your $20 after everything's over. So anyway, so let's not point this at your face or anything, because this is a very old rubber band. But we're going to expand this rubber band. And let us set it up in such a way that every centimeter doubles. You could do that. Physically, something could be a property of this rubber that causes every centimeter to double in 1 second, let's say. And let's take two ping pong balls that were initially more than 186,000 miles apart. Now, I can't show you that in this room because the room isn't big enough, but take two ping pong balls in a very big universe that were initially more than 186,000 miles apart. Stretch the universe by a factor of 2 in 1 second. They will be now more than an additional 186,000 miles apart, and they will have moved apart then by a speed exceeding that of light. That's not a violation of relativity, because you cannot use that expansion of space itself to transmit any information from that galaxy to the other one or to any other. That is simply a property of space. So in fact, space can easily expand faster than the speed of light, and physics doesn't break down. Thank you, Alexander. Yes, in the back there.
Speak a little more about Hubble's likely preservation.
Hubble and its likely preservation. Yeah, this is a very touchy subject. So as to cover a lot of questions, I won't spend half an hour on this, although I easily could. I think Hubble has been a marvelously productive telescope and could remain marvelously productive if the fourth, planned for many years, servicing mission were to be done, which would replace the gyroscopes and replace the battery and also put several new wonderful instruments into the Hubble. Indeed, over its 15 years existence, Hubble has gotten progressively better because we have replaced aging old technology instruments with newer, better ones. The argument that has been made against the servicing of Hubble has been first that it's too dangerous for astronauts, which I do not buy, because NASA is not scrapping the shuttle. It is trying to revitalize the space shuttle in order to go to the International Space Station. So if you're going to take 24 trips to the International Space Station, you might as well take one to the Hubble to fix this fantastic instrument. It turns out that a detailed analysis shows that it's only marginally more dangerous to go to the Hubble than it is to the space station. So then you could say, well, we can't afford it. Costs $2 billion. Well, yeah, big science costs a lot of money. But in the past, most of those $2 billion were simply absorbed by the NASA budget. This is what they do. NASA sends things up into space so that people can do science. The cost to astronomy, in a sense, has been $300 million, which astronomers, in most cases, I think Netta will agree with me, still feel is worth the cost. Now, if suddenly astronomers are going to be charged $2 billion for this refurbishment, and that will be taken from other planned space-based astrophysics missions, then I'm not so sure we should be sinking our money into the refurbishment of Hubble, because there's lots of other good things that are going to be happening in the future. But those $2 billion had been grandfathered in by past administrations. And so why should we be charged now for this refurbishment? So I'm in favor of refurbishing Hubble at a cost to astronomy of $300 million or so, and the gains, the scientific gains we will make will be fantastic. I'm not necessarily in favor of refurbishing Hubble if they're going to charge us for every dime and penny that's spent in association with things that NASA does anyway, and that is launching things into space. Okay? So there was a question there. Yeah. That's okay. I like questions from all walks of life.
Recently, I heard about the two stars, the one that was absorbed into the black hole, and the one that's being ejected out of the Milky Way. Supernovas, which all of these things, in my mind, are cataclysmic events.
That's right, yeah.
Don't they have any type of effect, a net effect on the universe? I mean, and again, this is probably
floating
a
stars have
stupid
tremendous
idea.
effect on the universe, yeah.
But
the
even
very
that-
elements of which you are made were ejected by exploding stars, and in many cases even cooked up during the explosion. If all stars were like the sun, which will remain these stable white dwarfs essentially forever, then even though the sun is right now cooking up helium out of hydrogen and will someday cook up carbon and oxygen out of that helium, if all that carbon and oxygen always stayed bound within stars, it would never become available as the raw materials for life itself. So some stars had better explode. Then, aside from that, though, yeah, stars exploding, they heat up the space between the gases between the stars, and they cause galactic fountains. They also send shock waves through space, which can trigger the formation of new stars from clouds of gas that are on the brink of gravitational instability. And then some star can explode nearby and push it over that brink, and hence lead to new star formation. And they give rise to neutron stars and black holes. So I think these explosive phenomena have a profound effect on the cosmos.
But could they net effect as far as that type of energy that you were talking about?
Oh, could they produce this dark energy? No, we don't think so. We think this dark energy is much more fundamental and doesn't come from any kind of an explosion. Yes?
Is that our universe is affected by multiverses outside the universe?
Yeah. So the question, because you're kind of fading in and out there are these hypotheses that there are other universes or brains out there. And it's conceivable that they are affecting us. This is now in the realm of this area called string theory. Perhaps Brian Greene will talk about this aspect of it in April when he comes here. But it is conceivable that these other universes or brains leak gravitons, the carriers of the gravitational force, back and forth. Okay? So it's conceivable that they are having an effect on us, and that what this acceleration really is maybe is either other universes pulling out on us, but there I don't understand how that would explain the energy density that we appear to measure as a result of WMAP. So there are other ideas. Maybe gravity is leaking out of our universe over large scales, causing essentially a weakening of gravity, which could cause this acceleration. Again, I'm not a theorist. I don't really know how to interpret this. I know which end of the telescope to look through, so to speak. And I don't quite understand these theories. When I go to conferences of these people talking, they're smart and all that, but my eyes just glaze over. I just don't understand what they're saying. So I need a good public talk so that they explain to me what it is they're talking about. But what I don't understand is how they account for all of the observations. Certain subsets, like acceleration, might be due to a pulling from the outside. But how does that affect what I think is a clean measurement of the density of stuff within our universe? So to me, they've never completely explained that. Yes, back there. Go ahead. Mm-hmm.
Since acceleration is normally caused by heat, does that mean the universe is heating up as well as accelerating?
Okay, so you said acceleration is caused by heat. It's not caused by heat of the classical sense. I mean, that's a very interesting question. You've had interesting questions all 3 evenings, actually. This energy is not associated with the random motions of particles, which is how we normally describe heat. It's either a property of space itself through these quantum fluctuations, which again are not really heat. They're a property of quantum physics, really. Quantum mechanics demands the presence of these fluctuations. Otherwise, we would know the energy of every point in space at all times, and that's forbidden, it turns out. So none of these things can be thought of as real heat. Instead, this expansion is causing whatever stuff is already in the universe, like the particles within it and the microwave radio photons, to become ever more dilute. So in fact, the temperature of the universe is decreasing with time, and in fact, because of this acceleration, it's decreasing faster with time than it would have been had there been no acceleration. Yes?
I understand that the age of galaxy creation was about 8 to 10 billion years ago, roughly.
Galaxy
creation, 8 to 10 billion years ago.
Yeah.
But now they're finding that is also an acceleration of galaxies 2 to 3 billion years ago. Is it possible that is another idea besides dark energy, that as you create the number of galaxies, they're pushing one another apart?
Well, that's an interesting idea. Most galaxies actually started their formation even beyond 8 to 10 billion years ago. We see fragments of galaxies even 11 or 12 billion years ago. So I would say most galaxy formation and even the aggregation of little bits of galaxies to form bigger galaxies, that all happened quite some time ago. And now what's happening is clusters of galaxies are still growing, but the number of individual galaxies does not appear to have increased very much in the past 4 billion years. In other words, during this accelerating era of the universe. So it's unlikely that creation of galaxies could explain this effect.
Professor, in discussing Hubble's law, you used the word presently a few times.
Yes.
In describing how objects that are further away are presently moving away more quickly. But we don't observe objects further away at the present time.
Yes, yes.
How do those two...
The reason I was careful to say present is that some people say, oh, Hubble's law is that the speed of recession is some proportionality constant, now known as Hubble's constant, times the distance. So they then say, aha, the logical conclusion is that as the distance of a given galaxy increases, its speed increases, right? If a constant times distance equals the speed, then as the distance increases, the speed must increase, and therefore Hubble's law already implies an accelerating universe. It most certainly does not. Hubble's law simply says that at any given time, and I simply use the present, the more distant galaxies move faster, independently of any decelerating or accelerating phase. Now, to get to the second part of your question, how do we measure the present time? Well, look, that's a very interesting point you've made, but if we measure the distances of galaxies that are only 100 million light years away, okay, we're seeing them as they were 100 million years ago. That's small out of the 14 billion year history of the universe. So Hubble's law is defined by galaxies that are sufficiently far away that they're not bound to ours like Andromeda is, so in which case the space isn't really expanding at all, but not so far away that you have to start taking into account the fact that you're looking back in time. Hubble's law, as measured, the linear relationship is measured by the galaxies which are at the Goldilocks distance of being observed at essentially the present time, but not so close that you have to worry about other, murky factors that mess up the relationship. But that's a very interesting question.
Maybe we'll take one last question,
Then, yeah.
Filippenko is happy to personally ask.
Or I could even stay up here, but people who need to leave can leave. Sure. Mm-hmm.
Yes.
That universe, billions later, that
Billions of years later from now.
yeah,
Okay.
They'll become.
Oh, will the universe have nothing in it?
Yeah.
Well, not really. I mean, it'll expand faster and faster with time. And so think about a whole bunch of marbles in a box, okay? Box gets bigger, number of marbles stays the same. But the number of marbles per unit volume in that box, per, cubic inch or something like that, decreases. So the point is that the density of matter in the universe is decreasing. But it's not completely empty, nor will it ever be completely empty. All right. Now, someday this dark energy, whose density we think is staying constant or nearly constant with time, even though the universe is expanding, the amount of the stuff per unit volume is staying the same, so the amount of stuff is actually growing. It could be that someday this stuff will turn into more normal stuff. Now, that sounds weird, but we actually think that you and I and everyone else may have come long, long ago, fundamentally, from a dark energy, kind of analogous to what we're talking about now. But this dark energy that I'm talking about at this moment, in the early universe, sorry, I got convoluted there, the energy I'm talking about that existed long ago, we think expanded the universe by a tremendous amount. It inflated the universe. Then that version of dark energy stopped becoming dark energy and it turned into normal stuff. You and I. So maybe the dark energy that we have right now will turn into normal stuff later on, and in that case, in fact, the density of normal stuff will increase. So I would say anything goes at this point. But definitely the universe will never be completely empty because there's stuff in it right now. And as far as we know from the laws of physics, the stuff that exists now will never completely go away. It'll just be very diluted in an enormous volume.
On that exciting note, let's thank Alex.
Thank you very much.